In the last week's videos, we discussed that we can represent trees by linked list, which is you basically have a struct node representing each node of a tree, and you can connect each of the nodes with another node. Today, we are going to see one more type of representation. I didn't cover this previous week because this is not too oftenly used, and you'll see a reason why it isn't. So this is the array representation. So as you can see, we have an array that stores the entire tree. And how it works is the zeroth index of the array is always empty. And the first index stores the root always. And the next two indexes store the left and right children of the root. So if you try to represent a tree in this form, usually we store all the indices in this form, which is if we have an index I that denotes a parent node, then its children are denoted by 2i and 2i plus 1 indices, which is, let's say if 25 is on index 1. Now, if we calculate 2 into 1, which is 2 and 3, we can see that the children of 2 of the node 25 will be at index 2 and 3. Now, a problem with this approach is that there might be no children to a particular node. Like in this case, 2 has no children. So we see that like 2 is at index 2, so the childs will be at 4 and 5. And we see in our array that 4 and 5 are empty. So basically, we are wasting a lot of space, especially for sparse trees, which do not have a lot of children. So this approach makes a lot more sense when we talk about perfect trees. So just a reminder, what are perfect trees? Which are trees which are filled at level L, which are completely filled at level L, which is they have both children at each level. So 25 will have two children, so 2 will have two children, and so on. So this is an example of a perfect tree. So in that case, an array representation makes sense because we are not wasting any space. Um, but like last time, we covered the second way, which was the linked representation. In this representation, we store basically pointers to left and right, and there's no space. We do not waste any space. But now the overhead is we are storing pointers in this case to the left and right node apart from the values. So this approach, this array-based approach, is useful in some data structures related to trees. Like whenever we cover some dense type of trees like heaps, you're going to see that we are going to use this representation, the array one, but mostly linked representations are more frequently used to represent different types of trees. So now we are going to discuss some of the use cases of traversals. So last week we covered a few ways to traverse our entire tree, which was both a depth first search and level first search or breadth first search. But we didn't cover like why is that important. So I just wanted to give you a glimpse of like all the traversals have specific use cases. For level order or in order, it should be pretty intuitive. Like in order of a BST can yield you a sorted tree, while level order could be another form of operation. But sometimes students find difficulty in understanding where pre-order or post-order makes sense. So I have a few use cases here, which is I have this file system, which is I have this folder called pre-order. This has three different folders, 1, 2, and 3. And within this pre-order folder, I have one text file, while within the folder 1 and 2, I have like three different text files. So one has b.text, 2 has c.text, and d.text. So this is an actual folder on my system that I just created. And you can see like if you type like the ls command on Linux or the ls command on PowerShell, by reaching this particular folder, which is like pre-order is acting as a root, you can see like I have these three folders. But let's say if I want to find out what are the constituents of this folder, we'll follow this command like ls-r. Ls is basically like listing directories. So if you go to a particular location in your command line, and if you type the command ls, it will state all the folders or files that are there in that directory. But let's say if you want to recursively find what are the files or folders within the folders itself, so in that case, pre-order traversal makes a lot of sense, which is printing the directory listings. So if you type the command like ls-r, it not only prints what's at the current directory, like it's not only printing 123 and a.text, but now it goes into each of these folders and prints what is there in the folder. Like at 1 it's printing b.text, at 2 it's printing c and d.text. So let's say if you are creating a program that represents a file system and you want to print the directory listings such that you print the root node, which is pre-order, which is called pre-order. It's basically string, like all these nodes have values in the form of strings. So you can print this in this form, which is you print the root element and then there is some sort of a space or a tab across levels. Next, you're going to print its children. So how do pre-orders work? Pre-orders will basically work, which is we have this root left right. So technically it prints the root, which is pre-order right here. Next, it goes to the left. So in this case, it will go to the left. This will now be the new root. It will print this new root. Next, it will go further down. It will make this the new root. It will print this new root. Next, it will go back up. Now this doesn't have any right child, so nothing happens. It goes to the next child, which is this 2. It prints 2 because now that's the root. It's going to print the left and right childs, which is right here. And then it's going to go back up. So this is one example of a pre-order traversal. What about post-order traversals? So post-order traversals are also helpful in some cases. Like in this case, I'm calculating what are the file sizes of a particular folder. And I want to uh, display these file sizes in the form of this format, which is you have this first folder that has 100, the file size is 100. The second folder, the file size is, it has two files, both of them has 200 and 300. And the third folder has the total file size of 500 because it has just one file a.txt, so it kind of stores just one value, which is 500. So if you wanted to print what are these file sizes in these recursive folders, you can use a post order traversal, because typically how post orders work is you have left, right, and root. So it first goes, like when we start with this as the root element, it first goes to the left. So it first next goes to the left. Now this file particularly has some file size which is 100, and this is going to be returned back to the parent element, which is you first traverse the children and then the parent. So in this case, since there is no right child, 100 will be returned back to the parent. So that's how we calculate the sizes of different folders. So basically, like next, when it goes back up, root is still not getting printed. It will go to the left. It will further go to the left. Now it will calculate left and right sum, which is 500. It will return back to its parent. So you can print the size of a folder. Similarly, like this has no children, so no file sizes, so it's typically 0. And then a.txt has one value, which is just 500, which is going to be returned back. And all of these values are going to be summed up back in the post order traversal, which is a program like this could be made pretty easily by using a post order traversal. So you can see my final output would be like the total size of the folder is like 1100 kilobytes or something like that. In the next video, we are going to discuss what are the different properties that are related to height, which will give us kind of a segue into the AVL trees.